Good morning.
Morning, sir.
Yeah. So, welcome to lecture number 11, and we'll be starting with some different varieties of cache. So, in the last class, we discussed about the direct mapped cache, wherein the word, the adjective direct for that caching came from the point that when I have an address, I use some part of that address. In the previous case, I had a 5-bit address and I used, so I had a 32 location RAM and a 8 location cache. To address this 32 location RAM, we need 5 bits. The last 3 bits, or the least significant 3 bits, were used to index into the cache, while these 2 bits, the most significant 2 bits, were used as a tag. And since I am directly using an address without any manipulation, I am directly using some bits of that address to index into the cache and some other bits for the tag. This type of cache organization is called direct mapped cache organization. We also saw the difference between write through and write back policies in cache. Today we will address some difficulties or disadvantages of the direct mapped cache organization, and then we will take the next step forward of how do we come out of these difficulties. So when we take the last organization or the direct mapped organization, note that all the addresses, the 32 addresses in the RAM starting from 0 to 31 can be actually grouped into 4 classes: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So, so let me even complete so that it is very straightforward for you to look into this and understand that all the addresses, all the addresses of the RAM which will map on or to the same location in the cache, all the addresses in the RAM that will map on to the same location in the class, in the cache, they are grouped. So when I take all the addresses in the RAM and group them according to the location they will map on to the cache, now note that if I have a 32 location RAM and a 4 location cache, this would be the grouping. So this will all map on to the 0th location of the cache, this will map on to the first location of the cache, and this to the second location, and this to the third location. So the locations in the cache basically are being used or potentially can be used by a set of memory addresses, and note that larger this list, the chance that a cache entry essentially gets rewritten is very high. For example, the 0th location in this cache is shared by 8 addresses. So first I have 0 in the cache, I bring say location 8 into the cache. The moment I bring 12, this 8 gets erased. The moment I bring say 20, the 12 gets erased. So if this list is very long, say 100 addresses, then the chance that the data or the instruction or whatever I have brought into the cache gets erased very quickly becomes very high. Right? So this is one big disadvantage of direct mapped cache. If at all you write a program that will access first 0, then 4, then 8, then 12, then 16, every time the program is accessing memory, there will be a cache miss, because that particular location will not be there in the memory. So if you take this, though there are 4 locations in the cache, this is the cache, though there are 4 locations numbered 0, 1, 2, 3, if I have a program that will access 0 first, then say 4 next, 8 next, 12, 16, 20, 24, 28, the 0 will map on to here. Next time 4 is fetched, this 0 will be erased and 4 will be fetched. Similarly next 8, then next to 12 and so on. Though I have 3 locations that are empty, if my access pattern is going to be like this, though the cache is not full, still I will have cache misses, and this is one disadvantage of having a direct mapped cache. Now how will we go and get out of this disadvantage? So again I recap, in the examples that I have just mentioned, there were 4 locations in the cache and 3 of them were always empty. Because of my access pattern, though the cache was not full, still I was getting 100% cache misses, essentially degrading the performance. How will I get out of this problem? The way you can get out of this problem is to use something called an associative memory. Or we can now call it as fully associative memory. The moment I say fully associative memory, there is something called partially associative memory. We will come to that little later. What did we do in the cache? In the normal cache, which had 4 locations as I told you, whenever I want to access an address, say I want to access address 8, 8 maps onto the location 0. So I go into the 0th location, and ask, are you storing 8? If it says yes, then it's a cache hit. If it says no, then it is a cache miss. So I now look, nothing is stored here. So I fetch 8, it's a cache miss, and I put 8. Now suppose I want to access 9. I know that it's going to be stored on the first location in the cache. I go to the first location and ask, do you store address 9? No. Then I fetch 9. So every time what I do with the cache, I take the address, then I find where that address maps on to which location in the cache, go to that location and find if that address, the value corresponding to that address is stored or not. So the way I am accessing cache, this cache is the directly mapped cache is based on the address. I repeat, the way I access this direct mapped cache is based on the address that is generated by the CPU. Again I repeat, when I want to say access address 12 in the RAM, the hardware now looks that 12 is mapped on to the 0th location in the cache. It will go to the 0th location and see if the address 12 is stored here. The content of address 12 is stored here. No, here only the content of address 8 is stored. So this is a cache miss. Now it will go and rewrite this with the content of address 12. So the way I am accessing the normal cache, again I repeat, is based on the address generated by the CPU. That address is basically used to index into the cache and find out whether that particular address value, the content of that address is stored in the cache. If it is stored, it is a cache miss. If it is not stored, it's a cache miss. And then I go and fetch that value. So this is the organization of a normal direct mapped cache. Now the cache that I am going, so the drawback of this, again I repeat, though there are 4 locations, if I am going to access first 0, then 4, then 8, then 12, then 16, then 24, then 20, 24, 28. If I am going to access in this way, though there are 3 locations in the cache, this will never get full because none of the address that I have accessed so far maps onto 0. Correct? So, so the drawback is that though 3/4 of the cache was always empty, I was getting cache miss because of the access pattern. Now to get, this is a major disadvantage of directly mapped cache, and now to get out of this disadvantage, we now propose something called a fully associative memory. In a fully associative memory, any address can be mapped onto any location. Unlike the direct mapped cache, wherein to the 0th location only these addresses can be mapped. To the first location only these addresses could be mapped. For the second location only these addresses could be mapped, and third, so on and so forth. But in a fully associative memory, any location its value can be stored in any location in the RAM. The value of any location in the RAM can be stored in any location in the cache. So if I have a 4 location cache, fully associative memory, or we can call it as fully associative cache. If I have a 4 location fully associative cache, I can store any location anywhere here. So first I am accessing location number 0, I store it here. Now I am storing the content of the location 0 here. This is address in the RAM. If the RAM stores some value, that value in location 0, that value will be loaded. Now when I am accessing 4, the 4 can be stored here. Then I am accessing 13, 13 can be stored here. When I am accessing 12, 12 could be stored here. Now the cache essentially is fully utilized, right? So any address can be stored anywhere in the cache. If any address could be stored anywhere in the cache, how will the processor access that cache? How will the processor read from the cache? Suppose the processor is trying to access, say, 4. In the previous case, it will go to location 0 and ask, is 4 stored there? It will go and check if 4 is stored there. Now what will the cache do? What will the processor do? It will go to the cache and ask, is 4 stored anywhere? If the cache says yes, it is stored, then it will take the value. If it says no, then it has to go to memory and fetch it. So there is a difference between how the cache was accessed in the case of direct mapped versus how the cache is currently accessed in the case of fully associative cache. In the previous case, the address was given, that address mapped onto a specific location, so you know the location where the particular address can be stored, and you go to the exactly to that location and find out if the address is stored there. If it is not, you decide it's a cache miss. If it is, then you say it's a cache hit. But in the case of fully associative memory or fully associative cache, what do? You go to the memory and ask, is this particular location stored anywhere in that memory? If it says yes, then you take its content. Otherwise, it's a cache miss and you go back to the main processor. Okay, right? So what are you doing here? In the case of fully associative cache, I go and ask whether a particular address is stored. So I go and address its content. What is its content here? The address 0, 4, 13, 12 along with the values of those. I go and ask if this particular location is there in your contents. So this particular fully associative cache is also called as content addressable memory. The abbreviation is CAM, CAM, CAM. Okay. So when I have a content addressable memory, I basically get away from the problem of very less cache utilization as we had witnessed in the case of direct map memory. But the problem that we will face with content addressable memory is that the functionality is too complex. The functionality is too complex means that I can store any address of the RAM at any location. So if I go and ask the CAM, is this particular address stored in your cache, then it has to search all the locations and then give me an answer yes or no. For it to search all the location, the hardware required to implement that searching very quickly. It can't take another hundreds of cycles to search all the location and give me an answer. It has to do it very fast. So the hardware actually required to search all the locations and finally decide whether it is stored or not, correct? That hardware is very huge. It consumes lot of power and area. So the problem is that for me to actually implement a content addressable memory of very large size, as I told you, the cache today can go up to MB. If I want 1 MB of direct mapped cache, it is going to be straightforward to implement in a processor. But suppose I want a 1 MB of content addressable memory, it itself becomes a huge hardware by itself, and it consumes lot of power and it can potentially consume lot of area. So because of this, implementing large sized content addressable memory inside the chip becomes extremely complex. But you have certainly an advantage that you can utilize this memory, thereby what do you get? So let me just conclude this CAM versus direct mapped cache with this example, which I have been repeating, but I am again doing it once or twice because this is one concept that students quite miss. So let me conclude this. So this is direct mapped and this is content addressable memory. Both have 4 locations. Suppose I am accessing 0, 4, 8, 12, 16, 20, 24, 28. When I am doing this direct mapped cache, I will have 8 cache misses. Suppose I am accessing it like this. 04812, 04812. I am accessing the first 4 locations followed by again the first same locations. This will give me 8 cache misses, but in the CAM 0 will be loaded, 4, 8, 12. The next time I am accessing 0, 4, 8, 12, it is going to give me 0 cache miss. So in the case of CAM, this will only give me 4 cache misses. So this immediately you get a 50% improvement. Suppose this is going to be executed say a million times. The 0, 4, 8, 12 is going to be accessed in this sequence say 1 million times. So this will give me some 4 million cache misses, while this will give me only 4 cache misses. If the 0, 4, 8, 12 it's a loop and it is accessed say 1 million times, every time it's a cache miss in the case of direct map, it's going to give me 4 million cache misses, while this will only give me 4 cache misses. So first time 0, 4, 8, 12 is fetched, it is stored here, and consequently it is going to remain like this. So this is the big advantage of direct map memory. Big advantage of CAM over DM. But the problem is that the CAM is too difficult to be implemented on a chip, and the reason is that it occupies lot of area, and it also consumes lot of power. So in your mobile phone, if I put a CAM, then every alternate phone calls you have to go and recharge your chip. So that's the implication. To be very naive, that could be a very practical issue. Now what will we do? So we want to have the best of both. I need to have cache which will not occupy that much area. It can occupy some area, but it should not occupy that much area. I also need it to be utilized fast, to be utilized in a good fashion. So we come out with a concept of what we call as a set associative memory. This is a notion of what we call as a set associative memory. This is one, or set associative cache. So what is a set associative cache? It is a mixture of the directly mapped cache and the associative memory. It is a mixture of the directly mapped cache and the associative memory. Now let us look at how this works. What we are telling here is that the whole set of addresses in the random access memory is now split into 4 sets because of a direct mapping cache. Suppose I have 4 locations and say this is a direct mapped cache. Because of this direct mapping, your addresses in the RAM, namely we had 32 addresses, it got split into 4 sets. Within each set, I will implement a content addressable memory. So what I have is, in this cache, I have doubled the size of the cache. Now what I tell is that in the case of fully associative memory, what did we tell? Any address can go to any location. Now I am restricting that definition and saying any address within a set can go into any location within that set. So this is the cache, and so there are 4 locations 0, 1, 2, 3. Each location will have space to accommodate 2 addresses instead of 1. So suppose I am accessing 0, suppose I am accessing 8, 8 goes to this location. Now I am accessing 12. In the case of directly mapped, I will erase this 12 and put 8, but here 12 can go here. So any location or any address within a set, so there are 4 sets as you see here, any location within any address within a set can be stored in any of the location in that particular cache location. For example, here 8 can go stand here, 12 can go and sit here. Now 24 comes, say 24 is mapped here. Now 8 again comes, 8 goes here. So any address within a set can map onto any of the locations in this. For example, any address within the 0 set can map onto any of these locations in the 0th line of the cache. So we call these as lines. So this is line 0, line 1, line 2, line 3. These are called cache lines. So any location in a set can map onto any location within the corresponding cache line. So as you see now, there is a difference between the direct mapped cache and the set associative cache. What the main thing is, suppose I have something like an access pattern which is 0, 4, 0, 4, 0, 4, 0, 4. I am accessing like this. In the case of a direct mapped cache, you would have got 8 cache misses. In the case of a set associative cache with 2 cache lines, initially 0 will store here, 4 will store here, then there will be no cache misses. So you will have only 2 cache misses in the case of a direct mapped cache, a two-way set associative cache, cache with 2 locations per line, you will get 0 cache misses. So what we are doing here, there is a direct mapping. The moment I get an address, I go to which cache location it should be mapped, I go to that line. In that line I ask, hey, is this address stored? So I do a content addressable search, I do a associative search or whatever, I address based on the contents with respect to a single line. I don't do for the entire cache. So if I want to find out if 8 is stored, I go to the 0th line because 8 gets mapped onto the 0th line and ask, is 8 stored? So I do a direct mapping, and then the moment I do that mapping, I get the cache line number. In that line, I go and do a content addressable search. So this is how I merge the concept of a direct mapped cache and a fully associative cache to merge them and get this hybrid realization of what we call as a set associative cache. The name associative cache comes because I am doing a content addressable search here, and this is also called set associative because that content addressable search is restricted to a single set, as you see here, set of addresses, and that is how this name set associative cache comes into practice. Now let us go and see a bit more on this. Let us say that I am going to get a 4 location or now we could call it as 4-line 2-way set associative cache. Four-line 2-way set associative cache essentially means these are the ways. This is way 0, this is way 1, I will call it as W0, W1, and this is line 0, line 1, line 2, line 3. All the addresses that map on to line 0 can be stored in any of the locations here. All the addresses that map on to line 1 can be stored onto any of the addresses here, and so forth. So this is the organization. Now let us go to the next step. Suppose I am accessing say 1, where it will get mapped to? It will get mapped down to here. Now I am accessing 5, it gets mapped down to here. So let me write it down. You are accessing 1 followed by 5. Again you access 1, it is a cache hit, it is available. So again you access 1, yes, it is available. Now you are accessing 9. When you are accessing 9, which one will you replace? Do you replace 1 or you replace 5? In the previous case I did not have this choice, because there was only one. In the direct mapped cache there is only one location where each of these address can map. So in the previous thing, if I had 9 and there was a conflict, right, there was a conflict, then immediately I would have erased that 1 or 9 whatever was there. In the case of directly mapped cache, I will not have an option to go and find out what got erased. But in this case, which one should I erase? I don't have an option of what should I erase in the case of a directly mapped cache. But in the case of this set associative cache, now I have a choice. Should I erase 9 or should I erase 1? Should I erase 5 or should I erase 1? Now here, when you look at the access pattern, first I accessed 1, then I accessed 5, then I accessed 1 again and again, twice, then I am accessing 9. If I look at that access pattern, you see that this 1 is more frequently accessed or more recently accessed than 5. 5 was accessed some point, but 1 was more recently accessed. So between 1 and 5, by even looking at this pattern, you will feel that if I remove 5, it is better rather than removing 1. If I remove 1 first, there is always a chance that 1 will be accessed in the next few cycles. This concept also comes from the fact of what we call as locality of reference, which we had discussed in the earlier classes. I hope you remember locality of reference. So based on the locality of reference, we also see that there is a chance that 1 will be accessed quite in the next few cycles. There is a larger chance. So between 1 and 5, my choice would be for 5 to get replaced rather than 1, and that is basically motivated by the way the access patterns were and also by the concept of locality of reference, which we had seen in the earlier classes. So I will go and replace 5 with 9. I will go and replace 5 with 9. So always I will go and replace, to formalize what I have done here, always I will go and replace something that is least recently used. or what we call as LRU. I will go and replace something which is least recently used, or what we call as LRU. This LRU is nothing but what we dictates what should be replaced. So this is a cache replacement policy. A cache replacement policy. LRU is a cache replacement policy which basically tells you out of different locations that are there, which one should I replace. So between 1 and 5 I decide 9 because 9 as between 1 and 5 I decide 5 because 5 was more least recently used than 1. Okay. Now so this is a concept of a set associative cache. So now we will formalize this entire procedure of set associative cache. Suppose I have a memory RAM with 2 power n locations. RAM with 2 power n locations, this will have n bits for addressing. It will have n bits for addressing. It needs n bits for addressing. Suppose I have a cache which has 2 power k locations. Now you need, so for me to index into the cache, out of this n bits, say let me say this n bits are a n minus 1, a n minus 2 till a 0. To index I will use a k minus 1, a k minus 2 to a 0. These k bits will be used for index, and for the tag we will be using the remaining n minus k bits starting from a n minus 1, a n minus 2 till a k. Okay. Now this cache, if it has, say it is an R way, that means I will have, the cache would be like this. So it will be way 0, way 1 till way r minus 1, and totally there will be addresses, indexes starting from 0, 1 to 2 power k minus 1. So this would be a cache 2 power k location cache with r ways, and this is how a 2 power n location memory can be mapped on to a 2 power k location cache with r ways. Okay. So this is to summarize what we have done so far. Okay. So now let us go and look at some performance issues. Now I define some parameters called cache hit. or this is also called as hit rate, or I call it as say tau. This is nothing but in 100 accesses how many were cache hits. Or how to this, just to give you an initial definition of this hit rate. In other words, the hit rate is nothing but what percentage of memory access or cache hits. So miss rate so since I am saying what percentage, I could basically represent it in the range 0 to 1. 100% means 1, 0% is 0, so 95% would be 0.95 and so on. So the miss rate is nothing but 1 minus hit rate. If I know what percentage of memory accesses are cache hits, I will know what percentage of memory access miss. That will be 100 minus that percentage. If you normalize it to a scale of 0 to 1, it is going to be 1 minus hit rate. So we have defined two things here, the hit rate and the miss rate. The hit rate and the miss rate. Now there is a program for which the hit rate is say 99%, or let me say the hit rate is tau. Let us go and work on a program. Tau is 0.95. Time to access a cache. Let me say it is 2 nanoseconds. Access a cache means is this location stored or not, to find out whether it is a cache hit or cache miss. That is the time required to access a cache and find out whether whatever you need is there or not. Let me say that is 2 nanoseconds. Time to access memory, the RAM, say let us say it is 200 nanoseconds, 100 times slower than the cache. Now suppose I have a program, right? What would be the time it spends on accessing memory? I'm looking at what you call as what would be the time the program on an average will spend on accessing memory. So I'm looking at this parameter, namely average memory access time, or AMAT. Average memory access time for this program, or any program that is going to execute with these parameters. Average memory access time is nothing but, suppose I have say 1000 accesses. What is average memory access time? What is the time required to access first? What is the time for the first access? What is the time for the second access? What is the time for the third access, and so on till what is the time for the 1000th access divided by 1000. This is what I mean by average memory access time. Right? What do I mean by averaging? I am accessing the memory as a program, I am accessing it 1000 times. What do you mean by the average memory access time? The time required to access it, the first I call it T1, time for the second which I call T2, then I sum up T1 plus T2 plus so on till T1000 divided by 1000, that is going to be my average memory access time. Now I want to have an estimate of this average memory access time. The estimate can be computed like this. You know that the cache hit would be 0.95. This you have experimented across different programs, and you know that the cache hit can be 0.95. I am just estimating, I don't even want an exact value for this average memory access time. I am making an estimation of this. In practice, when I use the processor, I find that the cache hit is 0.95. That means 950 of my accesses, 1000 access would only take 2 nanoseconds. The remaining 50 of them will take how many nanoseconds? Can you just on the video? I'll just ask. Can the GCT students answer this? The remaining 50 of them would take how many nanoseconds? Because the 50 will have cache miss, so the remaining 50 will take how many nanoseconds? Hello, are you able to hear us? Can you put your hands up if you can hear me? None of you can hear me? Can you wave your hand if you can hear me? Coimbatore. All of you know Tamil? Yes or no? I want to hear you. Can you wave your hand if you can hear me? Please wave your hand. I want to see some action. Only 2 of them can hear me, or all of you? Can all of you wave your hand? Okay, good. Now can you tell me what would be this memory access time for the remaining 50 accesses? Yeah, excellent. So some CM college has responded, it will take 202 units. It is not just 200 nanoseconds, it will take 202 nanoseconds. Why 202 nanoseconds? Because when I want the remaining 50 accesses, first it will go to the cache. It will spend the 2 nanoseconds to find out it is not there. Then it will go to the memory and access and come back. So it will spend 202 nanoseconds. So what is this total? This whole divided by 1000 this is plus 1900 by 1000. So this is 12,000 by 1000. So this would be 12 nanoseconds. So the average memory access time is 12 nanoseconds. If there was no cache, then it would have taken 200 into 1000, 200,000 nanoseconds, right? If there is a cache, since there is a cache, your thing would be 12 into 1000, which would be just 12,000 nanoseconds. So So this is how the average memory access time is calculated. So how do we calculate, so if I could make it as a formula, it is nothing but this 950 by 1000 is nothing but the hit rate into cache access time plus miss rate into memory access time plus cache access. So I can now say that this is cache as access time into hit rate plus miss rate cache access time into hit rate plus miss rate plus memory access time plus miss rate into memory access time. Now what is hit rate plus miss rate? Can somebody type on the screen in the chat? What is hit rate plus miss rate? Very good. DCRU. So can anybody else type it? Can everybody see this chat? Oh, everybody can see this chat. Okay. RVC, yes. So hit rate plus miss rate is 1. So this is now cache access time plus miss rate into memory access time. Okay. So this is the simple formula, simplified formula. So many books come to this level, they just give this formula, then they don't explain how it is arrived at. So please do note that this is how this formula is derived. So your average memory access time would be cache access time plus miss rate into memory access time. Now, okay, so we will stop here and we will continue in the next class. We'll have some 5 minutes for questions. If there are any questions, please do raise your hand. Okay, since there are no questions, so we'll meet next Wednesday. We will do a bit more on this cache organization, and then we will go and look at 2 more concepts, namely paging and segmentation in the next 2 or 3 classes. Thank you.